So today's talk will be a continuation of the talks on geometric algebra. So I'm going to share the screen now. If I can find the button. Here we are. You can see that.
Turn up your volume a bit.
I'll just shout louder, Scott.
That's better.
That's better. I'll shout. Okay. So we looked at the definition of a geometric algebra last time. So to remind you that basically you have algebra generators EI, and they satisfy EI squared is QI, where QI belongs to some field, usually the complex numbers, but the important thing is that the characteristic of F is not 2. And normally QI is an nth root of unities, but it doesn't have to be. But usually QI is plus or minus 1. So I'll just let Lou in. And of course, different generators anti-commute. So that's the other thing. EI and J is minus, provided I is. And then, so that obviously defines a product, but there's the wedge product. X wedge Y, and that's anti-symmetric, and there's a dot product X dot Y, which is symmetric. There's automorphism. Well, I won't go through definitions. There's an anti-automorphism, which is a transpose, and there's conjugation. X goes to X bar equals this alpha, which changes sign, and then transpose, and then the norm is X times X bar. Now, what I'll do now is to show how this works for what I might call the universal, or not the universe, that's wrong, the universe geometric algebra. So if we want to describe our three-dimensional real world as a physicist, then we take this algebra here. It's got generators 1, E1, E2, 3, and E1 squared equals E2 squared equals E3 squared equals 1. This anti-symmetric product here, relation. And alpha of a generator EI is minus EI, and because it's an automorphism, product of EI and J, which EI is J, is J. Well, actually, it's true. And of course, alpha E1, E2, 3 is minus E3. EI bar is minus EI. EI EJ bar is minus EI EJ. J. 3 bar is E3. So that's all you need to know for now. But we've got to interpret those generators. So we've got 4 orthogonal vector spaces. By orthogonal, they are orthogonal under the dot product. So it's GA0 plus GA1 plus GA2 plus GA3. And they're generated by, well, obviously GA0 is is R. We're assuming that the underlying field is R, and then we've got E1, E2, E3, and then their products. E1, 2. I'm using the notation that E1, 2 is E1 times 2, and so on. And E1, 2, 3 is just the product of all 3 of them. And we've got the following well-known algebras. GA0, let's say, is the real field. GA0 plus GA1 is isomorphic to 2 by 2 Hermitian matrices over complex numbers, C, by the representation onto Pauli matrices. So E1 normally this is denoted X, just switches coordinates. E2 is Y, and that's a 2 by 2 matrix, anti-diagonal minus I, and E3 goes to Z, which is diagonal 1 minus 1. So if we add them all together, A times the identity plus B times X plus C times Y plus E times Z, we get this matrix here, which is a general Hermitian matrix. So take conjugate, transpose. If we put A equal to 0, this is sometimes called a Pauli vector. I've no idea why. Perhaps somebody could tell me if they know. Excuse me. H bar is, you just take the X, Y, Z coordinates and negate them. And so the norm of H is H bar, which is A squared minus B squared plus E squared I, which happens to be the determinant of H. Slide. Now, so we've had the Pauli matrices. Now we get the quaternion algebra H. If we put I equal to E1 times E2, which is X goes to X times Y, this is diagonal I minus I, so that looks like quaternion. J is YZ, so it's I down, and K is minus 1, 1. And you find that it's that these matrices satisfy this, which is what we call quaternions. And the norm, just working out, is A squared plus B squared plus C squared plus D squared times the identity, which is again the determinant of this general matrix. So if n equals 1, then this matrix is unitary. Can I ask everybody to mute themselves? There's a duality in all these. Can everybody mute themselves, please, unless they want to ask a question? If we take the top generator, E1, 2, 3, and multiply it times an arbitrary element, X, we first of all get a linear isomorphism between the ground field R and these GA3, which are called pseudo scalars. So that's pseudoscalar, and the two inner algebras, that is between the Commission matrices. We have a mirror universe. If instead of taking the square of every e to be 1, we take it to be -1, then we get almost the same thing, except the order of the middle ones are different. We get the same alphas and the same bars, but this time GA0 plus GA1 is isomorphic to Quaternion algebra, and this one's isomorphic. So it's just switched around. Subgroups. Okay. So we'll let GA star denote the invertible elements of GA. Okay. So the smallest non-trivial subgroup we'll call Q, and this is the group generated by all the Qi in the field. If Q is finite, then by elementary Galois theory, Q is cyclic of E. We've seen that already. Q is plus or minus 1 for most cases. But, you know, this is interesting, you know, that you could use roots of unit. And let QE denote the subgroup generated by the signed basis element. So if you take QI being one of these things, Q and EJ, so that's one of the word, sorry, this is a monomial product. You get another group, and this is where I got it slightly wrong last time. For example, consider GA2 of R. So QE has 8 elements, plus or minus 1, plus or minus E1, plus or minus E2, plus or minus E2. And then if we take the dihedral group, D4, group of symmetries of a square, so write them like this. So alpha is a rotation through pi by 2, and beta is a reflection, not a diagonal, horizontally. And then, so these are all the 8 elements of D4. Alpha is of order 4, beta is of order 2, and alpha beta equals alpha cubed. So this is isomorphic in usually using that order to these elements of QE. So 1, E1, 2, minus 1, etc. And this induces a double cover from the group ring of D4 to R, which has kernel 1 and minus alpha squared. So I might have said that this is an isomorphism. That's my apology.
Just for clarity, alpha at the moment doesn't have anything to do with the alpha that you defined above.
Oh, which alpha?
When you were defining the algebra several pages earlier.
Oh, yeah.
So automorphism alpha.
That's an automorphism. Yeah, this is just an element of this group.
Right.
And this is true for all these GAs, that they are double covered by a group ring. So, and as you increase the index here, 2, 3, 4, etc., the groups you get are, you can easily write down a multiplication table for them in terms of previous ones. So it's easy to work out. Okay, so now we come to the Clifford group. So the Clifford group of a geometric algebra, we take all the invertible elements for which this, we do alpha x, so this is some sine of x. So I don't suppose it matters. Change the sign, it still is, I suppose, but anyway. And of course it's invertible, so it's like a conjugate of an element u in V, and you want the result again to be in V. Remember that V, V is just the this is G. So these are the one vectors. So that has a basis. So if this conjugation preserves these vectors, then that's called an element of the Clifford group. The special Clifford group is all those elements in the Clifford group which have even length. So, it could be across the brown field, or it could be elements like E1 times E2. And now, so we have a map from the Clifford group to orthogonal transformations of V given by this conjugation here. And we proved last week that the kernel of this map is F star. And if F equals R, the map is surjective by theorem of Cartan. I'll come back to that. I'm giving the definition now. Is the pin group of GA? Sorry,
Roger?
Yeah.
Your sound went out a minute ago. Could you explain what GA super E is again?
Oh, sorry.
Yeah.
These are all defined by elements of even length. So, so that E means yes. Sorry, I should have explained that. So, for instance, you know, typical element would be one. Well, generators E1, 2, E1, 2, 3, 4, and so on.
Okay, thank you.
Anyway, we're going to define pin and spin again, and look, I think that's the end of these notes. Now I need to open another. This.
We can't hear you, Roger.
Sorry, I'm not talking loud enough. Okay, can you hear me now?
Yes, thank you.
Okay, so this is what I've done here. I've cheated a bit. There's a paper by I'm going to refer to, which is a sort of write-up of the original paper by Attia et al., which is quite nice because it explains all the bits where they say it's obvious, but which isn't obvious to me. Okay, so this is, I've put this already in the notes, but it's Clifford algebras, Clifford groups, and generalizations of the quaternions, the pin and spin group by Jean Gallier. I assume he's French. So anyway, so let's go back. So we've had this definition already. Oh, he uses a different notation.
Roger, did you say you were putting it in the chat, the paper?
I've made a reference to it, but I can put the whole paper in if you want.
Yeah, please.
Yeah. You know, I mean, it's quite useful because it explains most things in kiddie form. So here's the definition again of pin. This time they've left out the sign, which is obviously you don't need. So sort of conjugate of a vector, and that again has got to be a vector. In this case, the vector space is Rn. So this is what he calls pin n, and nx, the norm of x is 1, and spin is where, but once again, his notation, this means all the even length elements. And CL means Clifford. Okay, so this is just a Clifford group of n. The field is R, and it's got n generators. Okay, and the square of everything, he starts off as somewhere here. For some reason, I've got 2 pages there, but the square, here we are. So he's assuming that the square is -1 rather than +1. Okay. So as I say, that's just a mirror image of this text. So, according to Attia, Bott, and Shapiro, that's the paper which is the use of the name pin is a joke due to Serre. Is this a typical French joke? I don't know.
Does anybody get it?
No. Oh, Jack does. Okay, right.
Jack, can you explain the joke?
Oh, you need to unmute yourself. Jack, you need to unmute. Okay.
Isn't it just pin and spin? I mean, it's silly. Is there anything deeper?
No, that sounds about right.
Yeah.
Special and not special.
Yeah. Yeah, that's right. And spin obviously means something to do with rotations. So, you know, but it also S for special. Yeah, it's sort of, yeah, okay. It's hardly going to bring the house down. Now, the theorem is that the restriction of rho, remember rho is the map which sends the Piner group to orthogonal transformations of Rn by this map here. And the kernel is -1, 1. And the restriction of rho to the spinor group, spin n, is a surjective homomorphism whose kernel is also -1, 1. Okay, so we know we've got this map rho, which goes from pin to O, and this is a homomorphism in the sense that all conjugations are homomorphisms. Now, by the Cartan-Dieudonné theorem, every isometry is a composition of hyperplane reflections, Sj. So we've got F is S1, Sj. And of course, these reflections are defined by by conjugating by an element wj, which we can assume is a normal vector by dividing out by its modulus and so on. So that's, you know, I mean, this is quite a it's a deep theorem. Does anybody know the proof? Anyway, that's why it's surjective. So, and this is also spin is the obviously by taking determinants or something. Spin is a product of an even number of projections. And so it says here, the group pin is generated by the unit vectors in Rn, so that's Sn minus 1. And every element of spin can be written as a product of even number of elements Sn minus 1. And the reader should verify that pin 1 is Z over 4Z, integers mod 4, and spin 1 is the integers mod 2. It's easy enough. What is pin 2? So this is a typical vector, AE1 plus BE2. It's got to have unit length, so A squared plus B squared equals 1. And it is a fact that any vector, if you have two vectors, say U and V and U inverse, I mean, assuming this vector is invertible, this belongs to these. That's I think they approved. So, sorry?
Would it be wrong to think of pin 2 as a Hopf link inside the 3 sphere?
Oh, well, it's. I think yes, it would, wouldn't it? That would be correct. Yeah. You see, this is the ones where we've got these are vectors in V. This one here. This is not, because this is an E1 times E2, but they also satisfy C squared plus D squared equals 1. So.
Yeah, I mean, I'm having trouble tracing through all the isomorphisms, but to me that looks very much like a Hopf link. For example, the quaternions live on such a Hopf link.
Yeah.
But carry on.
Okay. And as it's got here, it's a sum of two circles, U1 and U2, U1 plus U1. Circle in R2. It can also be shown that spin 3 is isomorphic to SU2, so that's special unitary.
Excuse me, in regards to, but I mean, this is a 4-dimensional vector space, and the first component of the first circle lives on the hyperplane of 2 directions, and the second circle lives on the other 2. So this would this not be unlinked, or it's a certain projection of it in,
Well, if pin 2 is a subgroup of SU2, then I think it's okay.
Okay.
SU2 would again be the 3 sphere.
Okay.
Right, now he takes a closer look at spin 2. So the Clifford algebra, CL2, this is what he means by Clifford algebra with two generators, E1 and E2, and E1 squared equals E2 squared equals -1. Okay, so here. Spin 2 consists of all products like this of vectors consisting of an even number of factors such that AI squared plus BI squared equals 1. And in fact, it's form well, he always makes quite a point of taking 1 to be the algebra 1 rather than the field 1, which is probably correct, but it seems a bit unnecessary from context. So you take x bar to be a, of course, it's a1 minus b2. So the norm is a squared plus b squared. And so this condition is 1. And the claim is that this does indeed belong to R2, which is the vector space, if x is in the Clifford group naught being either, right? So spin 2 consists of those elements x equals a1, b, 1, 2. We let I equals e1, e2. Remember, we looked at this earlier. I squared equals -1. E1i is minus e2. E2i is e1. And this is the turning piece. No. Oh, maybe not. And multiplying an element a plus bi by e1, we get the conjugate times e1, so as it passes through. And then he writes down explicitly what the action is. I don't think I need to go through all the pretty details, but it turns out to be a rotation, algebra, some theta is cos 2 theta. Written this as B1, of course, is a real number, and B2 is a real number, which is slightly confusing. But I guess it's just the coordinates. So this rho x is a rotation of angle 2 theta about the origin. This map here, B1, so multiplying by B1, and this V, of course, is B1 and B2. Establishes bijection between R2 and C2. And it's in general, spin n is a 2-to-1 cover of SON. SON is has fundamental group either Z or Z2, I think.
I'm sorry, Roger, I'm having a big misunderstanding. Spin 2 is U1, isn't that a circle?
Yeah, it's it's a rotation of angle 2 theta. So
right, but R2, I mean there's a set bijection there, but the circle and the plane don't look to be the same thing. So
Well, U1, you see, is the circle,
Yeah,
which it lies in R2.
right. But there's so there's not
Elements
a
of it
bijection between
rotate
R2. I mean, there's an embedding of
through
U1
an
inside
angle.
R2.
Sorry, I don't see what the problem is.
The establishes a bijection between R2 and spin 2. I don't get that that's
Oh, I see what you mean. Of course, they're different, aren't they? I don't know. Oh, yeah, I hadn't noticed that. I didn't write that. That this obviously is a mistake.
well, I mean, there may be a bijection between spin 2 and U1.
So yeah, this is yeah. Okay, well spotted. But spin 2 is definitely U1. I don't know. I think this should perhaps be rotations of R2.
Sure.
So maybe that was left out there. Okay. I'm glad somebody's awake. Yeah. And then he goes on to spin 3. Cliff algebra CL3 is generated by the 8 elements. As I say, this is the general 8-dimensional algebra. And we've gone through all this. Spin 3 consists of all even number of products of vectors, or one vectors, like this, and they all have length 1. Every such element can be written as, obviously, A times, well, A, B, C, D are real numbers. 1 is 1 of the algebra, and then E2, 3, E3, 1, 2. And this works, okay? We take the conjugate of X, which of course now he's got a capital X instead of a small x. So we are finding lots of misprints, and we get the norm of X is, as well, we've done this already, basically. So that lies on this 3 sphere. And once again, that all these, every element X in the Clifford algebra with an even number of elements generated by 3 elements, and it implies that this is also in R3, and it's also of length 1 as well. So so this is this conjugate is also CL31. So you can write. So the general element of these okay. I think we're going to prove that this lambda is 0. Write it like that, and then we take the bar of that, it's water, and take the bar of that, it's minus u minus lambda, which implies that lambda is 0, because it's got to be, the result has got to be, B is a vector, and this result has to be a vector, so that will only be true if lambda is 0. So spin 3 consists of those elements of this form. So remember, there's 3 generators here. These are like the unit quaternions, and of course we know that conjugation by spatial quaternions define a rotation of free space. This. Quaternions. So the rotation of SO3 induced by X in spin 3 can be used as rotation induced by this quaternion on your quaternion. Yeah. Then this is all lots of details, which I'm going to rush through a little bit. We've got spin 4 now, and I'll just state what cases we've got. In this case, we've got 2 lots of quaternions, taking the products. They satisfy this. So what do we get? Spin 4 consists of those elements of pairs of quaternions which satisfy this condition here, UU bar plus VB bar equals 1, so we lie sphere of dimension. Dimension 7. They also satisfy this condition here. So spin 4 is isomorphic to spin 2 cross spin 2 under this isomorphism given by here. So
I'm having a bit of a problem on that line.
yeah.
I'm sorry. I thought that spin 4 was isomorphic to SU2 cross SU2 earlier. And
Yes.
spin 3 is SU2, but I may just be remembering things incorrectly.
Yeah, that's what I would say actually as well. I'm wondering if this is another misprint.
Yes,
Yeah, yeah.
yes.
So I guess I should have. But I mean, it's his paper.
Wasn't
Yeah,
spin.
that looks better.
Yeah.
I mean, that looks like what he's proving too.
Then he's generally saying that if the norm of X is 1, so if the norm of X is 1, it's certainly invertible. Right? So, and it's in the Clifford group with n generators, it's even, then this conjugation is in Rn for all V in Rn if n is less than or equal to 5. Ian Porteous has written a book on this, so this is false for n equals 6. If we take x equals 1 over root 2 times 1 plus e1 into 6, then that is in CL 6 naught, and it's easy to see that n of x is 1, and yet apparently if you do this, you don't get a vector. You don't get something. Okay, this is good. I think we can get to a statement of the Carter-Bott theorem, or the Bott-Carter theorem. I think Carter proved that, sorry, not Carter. that's Scott. Cartan,
Cartan, maybe?
Cartan, no, Bott, B comes before C, so it's Bott, Cartan, although Cartan proved it first. Right. Obviously, there seems to be a lot of Americans don't read French. So let's take an orthogonal basis, and we have a quadratic form for which is got P plus squares and Q minus squares. And so PQ is, of course, the signature of this quadratic form, and it's P plus Q. So we define the group OPQ as the group of isometries which preserve this this form. So now we're looking at he has this problem that the norm of V is minus this, which may well be negative. So we allow elements X belonging to the Clifford group PQ with norm possibly +1, possibly -1. Okay, so this is the pin PQ is the group of X's in this. So we've got remember the algebra has got n generators. This quadratic form here, and the norm of X is ±1, and of course the spin group will be this, where this is the even. So well, oh yes, the spin, you see, it doesn't matter because the norm will always be. So, okay, so we have a row here. Restriction of row to the Piner group is a surjective homomorphism from pin PQ to OPQ. Okay, so this is orthogonal with respect to that quadratic form of Rn, and the kernel is the same proof, and the fact that it's surjective is also the same. So I'm not going to go through the details. The group pin PQ is generated by Sn minus 1 PQ, which means this here is the hypersurface, which is when all these elements are equal to 1. So if Q is 0, then it's a sphere, but otherwise it's some kind of I want to get in the last 10 minutes through periodicity. I have been through this, and it is fairly easy. And he does the early ones. Spin 1, 1 is, so this is lies on this hyperbola. Space the one. It's not connected. You all know hyperbola has 2 bits. Oh, so now we come to the periodicity. And apparently it was the period was observed by Élie Cartan in 1908, which is amazing. It's a long time ago. And as I say, Raoul Bott rediscovered it independently in the 1960s. So Anyway, it's not hard to show that this is C. So, just go over this notation. Rn and Cn for the algebra of n by n real matrices or complex matrices. And of course, there's also possibility of Hn, which is but n by n matrices with quaternion entries. This is true. He says it's not hard to show that. It's a bit tricky, but I'm sure you're all capable of doing that. And the key to the classification is the following lemma, that the Clifford algebra 0n+2 is isomorphic to the Clifford algebra n0 tensors with Clifford algebra 0.2. And if Clifford algebra n+2 0 Clifford algebra is the other way around, 0n tensor 0, and so on. And if I add 1 to each of p plus 1 and q plus 1, I get Clifford algebra PQ tensor with Clifford algebra 1. And I won't go through the details, but they're all here. I think it's correct, but no doubt Scott will find a mistake. And this is sort of a bit messy. It's something very similar in the paper file. I won't go through this. It shows that blah. So now we have the following isomorphisms. So the real n by n matrix, n by m matrices, tensor with the n by n matrices is the Rmn matrices. Well, you probably all know that from your student days. And Rn tensor over reals being moved back and forwards. K is C or quaternions. K has the entries in the n by n matrix, and then there's, so those first two are, well, he says they're quite obvious. I wouldn't say they're quite obvious, but they're not too difficult to prove. This one here is an oddity. It looks odd. If you take the tensor product of two complex numbers with themselves over R, it's the same as the direct product. And it gives the isomorphism here. And then and we want this one here, C tensor over R of H is 2, also here, and so then we can put all these results together. The dimension of C tensor, the C cross H, dimension over R, 2. So this is 2 by 2 complex matrices. So we have these isomorphisms here, which we've already talked about, and the Clifford algebra 0.8 is the same as the Clifford algebra 8.0, which is so 16 by 16 matrices with entries in R, and we have these isomorphisms here, and so have a look at this line here. you go CL0 n plus 8 is CL0 n plus 6 tensor CL0 2, and then you keep going down, 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 down until you get to CL0 n tensor CL2 0 2 0 2 2 0 2. CL0 2 is H, and CL2 0 is 2 by 2 matrices with real entries, and put it all together, and we get 16. And in second iso proof in similar fashion, and then we get the following table of CL0n for n equals 0 up to 8, given by that, and CLn0 is slightly different. This, they all end up as 16. And if you want to know what the Clifford groups are, small values of PQ that can be found in this reference. And we have this isomorphism here. Then we can also look at complex Clifford algebras, but I'm running out of time. I think if you're interested, you can look at this paper. Of course, all I can say is the quadratic form, if we're over the complex numbers, we can get rid of the minuses, and they're all plus. Then we've got more isomorphism here. Games. So that brings us pretty much to 6 o'clock. Are there any questions? Stunned silence.
What does this have to do with Bott periodicity?
Well, that is the periodicity.
Yeah, I think I was going to ask the same question. So Fred Cohen taught me a nursery rhyme which goes Z2, Z2, 0, Z, 0, 0, 0, Z, which has to do with homotopy groups of matrix groups.
Yeah, okay, that would require yet another talk.
But that, I mean, that's what I thought of as Bott periodicity.
Yeah, I mean, Attia and co go on to look at K-theory and how this refers to homotopy groups. So, as you say, that's what you understand as Bott periodicity. So, I guess that will maybe be the subject of another talk. Maybe you could give it, Scott.
Oh, thank you. I'd rather not.
That's a reward for asking the question.
Yeah. Never volunteer.
Dale asked the question.
Perhaps Dale could give a talk.
Jack has.
I have a reference question.
Yeah.
I know there's an old set of notes by John Milner on representation rings and pin and spin. Does anyone have a PDF copy of that? I don't seem to.
They're excellent notes. I don't have a copy.
Oh. I don't.
Well, if anyone bumps into their old copy of Milner's notes,
Milner's,
make a scan and send it to us.
so Milner's notes, is this a paper or just notes?
They were notes that were widely distributed in the old days.
Oh, yeah.
Can I ask about spin 4?
Sure.
So it splits as SU2 cross SU2.
Yeah.
As I understand it, the physicists say that all the physical particles in the universe see the left copy or the right copy. I think the left copy is the convention and not the right copy. I think we should be told. This sounds
to do with matter and antimatter?
Well, it has to do with chiral, and I don't know what chiral means actually. But so they, for example, there are people that have grant money to look for sterile neutrinos, I think, that live in the other SU2. This sounds crazy to me, and I'd like to understand it better. In particular, I'm just misunderstanding it completely.
Well, Lou might know, but you've asked.
No, I don't know how it works.
Yeah, well, it's bizarre to me that this should be the standard theory. It might not be. I might just be wrong.
So has anybody tried to turn this into diagrammatics the way that one would turn Frobenius algebras into diagrammatics?
Sounds like fun.
Well, once
Just
again,
wondered if somebody's done it.
Not I. Brian, any thoughts?
Nope. No, sorry.
Okay. Right. So next week, I think
Spectral complexes or something. I'm not 100% sure, but maybe spectral complexes and double complexes might have a way
have
more periodicity. Yeah.
Sorry. Can you say that again? So I don't know how to pronounce your names. Semi?
Yes. Maybe double complexes or spectral sequences, something along those lines might have a formulation, but I'm not too sure. Or for both periodicity, or at least after maybe passing from the homotopy groups to homology groups, maybe. But I don't know. It's a thought.
Does anybody want to comment on that? Well, it's certainly food for thought. So I'll finish there. I think next week Lou is going to talk. Is that correct, Lou?
I can, yes, all right.
Okay. So if there are no more questions, I'll see you all next week. Thank you.
Thank you.
Bye, everybody.
Roger, will you please remember to send your notes to me and I'll put them in the Dropbox.
I certainly will. Yeah.